Episode 106, titled Deep Model Families, CNN, RNN, LSTM, Autoencoders, GANs, Transformers, we focus on recognizing the major deep learning families by what structure they are designed to exploit. Deep models are not interchangeable just because they are all neural networks, because each family is built around assumptions about the shape of data and the kind of patterns that matter. When you match the model family to the structure of the input, you usually get better performance with less struggle, and you avoid chasing trends that add compute without adding value. The exam expects you to know what these families are used for at a practical level, not to derive their internals. In applied settings, especially in cybersecurity, you may encounter images, text, audio, and time sequences, and you need a mental map of which family fits which data form. This episode builds that map while emphasizing that model choice is an engineering match, not a popularity contest. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Convolutional neural networks, abbreviated as CNNs, are best known for images, but the deeper idea is that they are designed for spatial patterns and local structure. A convolution operation applies a small filter across an input grid, allowing the model to detect local patterns such as edges, textures, or repeating motifs in images. Because the same filter is used across different positions, the model shares parameters and learns features that are translation-friendly, meaning a pattern can be recognized even when it appears in different locations. This parameter sharing makes CNNs efficient and effective for high-dimensional spatial data, where learning separate weights for every position would be wasteful. The same local pattern principle can apply beyond images, such as in certain forms of audio spectrograms or structured sensor grids, because the key is locality. In security contexts, CNN-style thinking can also apply when you represent data in grid-like forms, such as heat maps or spatial embeddings, where local neighborhoods carry meaning. The practical takeaway is that CNNs are built to learn from local structure and spatial correlation. Recurrent neural networks, abbreviated as RNNs, are designed for sequences where order and memory matter, meaning the model needs to process inputs one step at a time while carrying context forward. In an RNN, each step receives the current input and a hidden state that summarizes prior context, producing a new hidden state that becomes the memory for the next step. This architecture matches problems where the meaning of an element depends on what came before, such as language, time series signals, or event logs. The key is that the model is not just looking at a bag of features, it is processing a stream where position and sequence influence interpretation. This makes RNNs useful for tasks like sequence classification, next step prediction, and modeling temporal dynamics in behavioral data. However, simple RNNs can struggle with long sequences because information can fade over many steps, which leads naturally to more advanced recurrent designs. The exam-level message is that RNNs are the classic family for ordered data and temporal dependence. Long short-term memory networks, abbreviated as LSTMs, are a type of recurrent network designed to handle longer dependencies by using gated memory mechanisms. The practical problem they address is that vanilla RNNs often have difficulty retaining information over many time steps, which can cause them to miss patterns that require long-range context. LSTMs introduce gates that control when information is stored, when it is forgotten, and when it is exposed to influence the next hidden state. You can think of these gates as learned switches that regulate memory, making it easier for the model to keep important signals and discard irrelevant noise across long sequences. This is particularly useful in language modeling, long-time series forecasting, and event sequences, where early signals may matter much later. While LSTMs are not the newest architecture, they remain conceptually important because they illustrate how adding structure to memory can solve training problems in sequential learning. At exam level, remembering that LSTMs are RNN-style models with gated memory for long dependencies is the core point. Autoencoders are neural networks trained to compress inputs into a smaller internal representation and then reconstruct the original input from that representation. The compression step forces the network to learn a representation that captures the most important structure in the data, because it must reconstruct the input using fewer internal degrees of freedom. This makes autoencoders useful for compression and denoising, where the goal is to remove noise and preserve meaningful signal. They are also useful for anomaly detection, because if the autoencoder is trained on normal data, it tends to reconstruct normal patterns well and reconstruct unusual patterns poorly, producing larger reconstruction error for anomalies. In operational contexts, this can be valuable when labeled anomalies are scarce, because you can train a model to learn normality and then flag deviations. The key is that the model is not directly predicting a label, but learning a representation through reconstruction. This representation can also be used as a feature input to other models, making autoencoders a general tool for representation learning in an unsupervised or self-supervised style. Generative adversarial networks, abbreviated as GANs, are designed for realistic synthetic generation through adversarial training, where two networks compete in a structured way. One network, often called the generator, tries to produce synthetic samples that look like real data, while another network, often called the discriminator, tries to distinguish real samples from generated ones. Training proceeds as a competition, with the generator improving to fool the discriminator and the discriminator improving to detect fakes, creating a dynamic that can produce highly realistic outputs. GANs became well known for image generation, but the deeper idea is that adversarial training can encourage sharp, realistic samples rather than blurred averages. The trade is that training can be unstable and sensitive to hyperparameters, because the two networks must remain balanced and neither can dominate too quickly. In professional settings, GANs are useful when you need high-fidelity synthetic data, but they require careful evaluation to ensure generated samples are valid and do not introduce artifacts. At exam level, the main recognition is that GANs generate realistic data by training a generator against a discriminator. Transformers are attention-based models designed to handle sequences and context by letting the model learn which parts of the input should influence each other directly. Instead of processing a sequence strictly step-by-step like a recurrent network, a transformer uses attention to compute relationships across all positions, allowing it to capture long-range dependencies efficiently. This is especially powerful in language, where meaning often depends on distant words, and in many sequence tasks where context is global rather than local. Attention gives the model a mechanism to focus on relevant tokens or time steps when forming internal representations, which supports both expressive modeling and parallel computation. Transformers have become a dominant family for many text tasks and increasingly for other modalities because they scale well with data and compute. The practical trade is that they often require more data and more training resources than smaller sequence models, and their size can create deployment challenges. The exam-level takeaway is that transformers model context through attention rather than through strict sequential memory. Mapping tasks across vision, text, audio, and time sequences becomes easier when you start from data structure rather than from model names. Vision tasks often align with CNNs because images have local spatial patterns and translation-friendly features, though transformers also appear in vision when data and compute are sufficient. Text tasks often align with transformers today because language depends on context and long-range relationships, though RNNs and LSTMs remain conceptually relevant for sequence processing. Audio can be treated as sequences over time or as time-frequency grids, which means either sequence models or CNN-style approaches can fit depending on representation. Time sequences in telemetry and logs often align with RNNs, LSTMs, or transformers, depending on sequence length and the importance of global context. Autoencoders can apply across many modalities when the goal is compression or anomaly detection rather than direct labeling. Practicing this mapping is about recognizing what the data demands and choosing the family built for that demand. It is also important to avoid using sequence models when simple aggregates capture the needed signal, because modeling order introduces complexity that may not deliver value. If the outcome depends mainly on counts, averages, or summary statistics over a window, a simpler model on those aggregated features can be more reliable, easier to train, and easier to govern. Sequence models are justified when the order, timing, and temporal dependencies contain information that summaries cannot capture, such as patterns of escalation, repeated attempts, or context-dependent transitions. If the sequence is long and noisy, but the signal is coarse, a sequence model can overfit or waste compute while offering little improvement. This is a common trap in operational analytics, where teams reach for sophisticated sequence architectures without first testing whether summary features suffice. The exam rewards the ability to choose simplicity when it captures the relevant signal. That choice reflects engineering discipline, not lack of sophistication. Training cost is a major consideration because transformers often require more data and compute to reach their full potential, especially when compared to smaller recurrent models or CNNs in certain settings. The attention mechanism can be computationally expensive for long sequences, and large transformer models often involve many parameters, which increases training time and hardware requirements. In practical terms, this means that model choice is partly an economic decision because the cost of training and iteration can be substantial. When data is limited, a transformer might not outperform a simpler sequence model, and the training cost may not be justified. Even when performance is better, you must consider whether the improvement matters enough to warrant the added cost. This is why model selection often includes a phased approach, starting with simpler baselines and scaling up only when evidence supports the investment. The exam expects you to acknowledge that transformers are powerful but often more expensive. Communicating model choice should emphasize matching structure, not chasing trends, because stakeholders need to understand why one family fits the data rather than why it is currently popular. ACNN is chosen because the data has local spatial structure. An RNN or LSTM because the data is a sequence where order matters. An autoencoder because the task is reconstruction and anomaly detection, a GAN because realistic generation is required, and a transformer because global context and long-range relationships are central. This structure-matching narrative is defensible because it ties the method to the problem rather than to hype. It also helps in governance because it clarifies what assumptions the model is making about the data. When you communicate choices this way, you make it easier to justify compute budgets and to explain why a simpler approach might be preferable. The best explanation is always that the model family was chosen to exploit the structure that carries the signal. Deployment constraints matter because model size directly impacts latency and cost, and deep model families can differ dramatically in inference burden. A small CNN or a modest recurrent model may run comfortably in real time, while a large transformer may require acceleration hardware and careful serving design to meet latency targets. Autoencoders for anomaly detection can be lightweight or heavy depending on architecture, and GAN generation can be computationally expensive if you need high-quality samples at scale. These constraints can determine whether a model is feasible in a production pipeline, especially when predictions must be made at high throughput. Operational cost includes memory footprint, compute per inference, and the complexity of monitoring and updating the model. This is why model selection is not purely an accuracy contest, because the most accurate model is not helpful if it cannot be deployed within constraints. Being able to mention latency and cost as part of model choice demonstrates practical maturity. The anchor memory for episode 106 is that CNN is spatial, RNN is sequence, transformer is attention, and autoencoder compresses. This anchor captures the core structure each family is designed to exploit, making it easy to map model to task quickly. CNN emphasizes local spatial pattern learning through shared filters. RNN emphasizes stepwise processing with memory for ordered sequences. Transformers emphasize attention to connect distant parts of a sequence and model context efficiently. Autoencoders emphasize representation learning through reconstruction, which supports compression and anomaly detection. LSTM fits inside the RNN family as gated memory for longer dependencies, and GANs stand out as adversarial generation. Keeping this anchor in mind helps you answer exam questions that ask which family fits a given data type or objective without getting lost in details. To conclude, episode 106, titled Deep Model Families, CNN, RNN, LSTM, Autoencoders, GANs, Transformers. Choose one family for one scenario and explain why in terms of structure. Suppose you want to detect anomalies in system telemetry where labeled incidents are scarce, but you have abundant examples of normal behavior, and you want a model that flags unusual patterns. An autoencoder is a strong fit because it can learn to reconstruct normal patterns and then use reconstruction error as a signal of deviation, which supports anomaly detection without requiring many labeled anomalies. If instead the task were classifying emails or messages where meaning depends on long-range context, a transformer would be a strong fit because attention can capture relationships among distant tokens. The justification in each case is the same style. You choose the family whose structure matches what carries signal in the data. When you can make that match explicitly, you demonstrate the exam-level competency of selecting deep model families by data shape, not by trend. Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.